Hi, Bob Ruckle here, speaking to you about some novel silicon resin-based mercapto functional materials and a use we've found for them to improve elongation and eventually some 3D printing applications. Let me share my screen here. I'd like to start by acknowledging my colleagues. So Tom Chung and Yan-Yun Lo do all of the applications work in the lab, and John Grand does all the synthesis work, at least for this project. And I get to come out and talk about it, or stay home and talk about it in this case. One of the applications we'd like to talk about is elongation in silicone polymers. If you use silicones a lot, you expect these materials to give you 300% elongation. That's typical in any kind of acid base or nucleophile electrophile condensation. Whether it's a homopolymer or a hybrid with an organic material, you should get something like 300% elongation. We've found that UV cured acrylate functional silicones typically give something more like 10%, and that can be quite disappointing if you're expecting the higher values. And the nice thing about the system we're showing you today is it does bring those numbers back up to about 200%. So just to exemplify that with some chemistry and data, these are silicone polymers that are functional on both ends, two different molecular weights, values of X, and they're reacted with a multifunctional silicone polymer and just standard acid-base conditions, so thermal cure. And just don't worry about all this other stuff, just focus on the elongation. The maximum here is over 300%. So that's pretty typical for silicones. Even in this case, it's a hybrid system, so we're reacting a silicone epoxy and hydroxyl. Hydroxyls react in with epoxy reactions quite easily. And we're reacting it with an organic epoxy system and really very similar conditions, so a thermal cure. And here what you see, even at or up to about 50% inclusion of the silicone, you get about 120% elongation. It's actually a bit on the low side, but it kind of makes the point. And the magic isn't thermal versus UV. This system, which is, again, epoxy and hydroxyl, is cured with UVA Cure 1500, which is an organic-based epoxy functional resin, and under UV conditions. So it's an acid-based cure, but UV initiated. And here you can see we get up over 300% elongation again. So it isn't UV, it is the functionality. We're pretty confident what's going on here is shown on this slide, or partially shown on this slide. The epoxy resin and the hydroxyl resins react, and the polymers are formed R1 and R2 in this sense. If one of those is a silicone, in this case R2, that silicone gets incorporated directly into the backbone, and the inherent flexibility of the silicone is conveyed to the hybrid polymer. So in this case, you get the high elongation. Just to show you first, before I show you the mechanism, this is an acrylate functional epoxy-based, so an organic acrylate resin, and reacted with a silicone resin down the bottom that's acrylate functional. And we use 0 to 80% of the organic and 0 to 80% of the silicone. And you see in red is elongation. Even at 60% silicone, we only get 6% elongation. And of course, what's happening is the acrylate material cures in a different way. The double bond forms the polymer, and the R group, which is shown over here, is not really part of that polymer. The polymer forms from the double bond. So we make the R group a silicone. It is there, but it is not part of that base polymer. The polymer's here. And we've shown in several publications over the last few years, if you use a di or trifunctional silicone, you can really help that. Even a urethane silicone hybrid gave improvement. We've been able to get this up to about 50% with these systems, but still nowhere near the 300%. So what we're talking about today is the Thiol Ene reaction. This is known to add just across double bonds. So if we have a polymer that's difunctional with the vinyl groups and a mercapto group or thiol group, it just adds across them so you get the functional polymer. And if that's a silicone, then that silicone is involved in that polymer. Of course, there's no cross-linking shown here. So if the R2 is a highly cross-linked system, which is what we're going to use today. You get the cross-linking from the R2 group and the elongation from the polymer. So before we talk about that, we need to understand a little bit of silicone jargon, and because I'm going to use that, it's really much easier to follow. So in this jargon, an M group is a silicon atom that has 3 methyls and 1 oxygen. So M for mono is a good way to memorize that. And a D group has 2 methyl groups and 2 oxygens, so di for 2. If you think about MDXM as the standard formula then for silicone or PDMS fluid. So you have methyls on the end or M groups on the end, and as many Ds as you want. That affects the viscosity, of course. And most of you are probably functional with T groups. They're used in trialkoxysilanes, where the oxygens are connected to alcohols that leave. So in this case, we have 1, 2, 3 oxygens and 1 methyl group. T for tri, good way to memorize that. And finally, we have Q groups. Q for quad, I suppose, but all 4 oxygens, no alkyl groups. This is the structure of maybe silica. So in MQ resins, which is what we're commonly talking about, you have mostly Q groups, maybe some T groups, giving you very high cross-link density, and the outer surface is covered with M groups. You can include D groups in there. We're not going to talk about that today. So this is the first chemical that I want to show you, and it's a little tricky. We'll go through it slowly though. This is a Q group here. It's got a silicon atom and 4 oxygens. So there are Y Q groups. And then this is the M group with 1 oxygen. There are X of those. And then we've added a T group here with 3 oxygens. That's functionalized with the mercapto. So that's shown with Z. If you just look at the Y to Z ratio, the structures we're going to use today have 0% Q, 10, 20, 30, 40, and 50% Q relative to the Z. The equivalent weights actually don't change a tremendous amount, but the viscosities go up dramatically. So you're getting very cross-linked systems. The other group we're going to look at is really equivalent chemistry, but with vinyl group instead of mercapto. So here we have the Q group, silicon surrounded by 4 oxygens. That's going to be the value of B, which we will arbitrarily set to 100 in all of these, just for ease of looking at them. And then A and C together are the M groups. Each of them has only 1 oxygen, and those are shown here. A and C usually adds up to 90 in most of these structures. And then the T group is down here. That's shown by D. We're going to set that to either 30 or 50 or towards the end of the talk 0, and we'll explain why we do that. You don't get as dramatic an effect on viscosity. You only get a factor of 10. So that's not as bad. The base formulation is shown here. We'll use the mercapto silicon functional resin and Somer Vin 65K, which is a 65,000 centistoke difunctional vinyl fluid. These are commercially available and used in a lot of systems. They extend that system to make it reasonably soft. Without that, it would just be intractable. And then the vinyl silicon resin that we just talked about. So we use these first and third materials to give you cross-link density, that second one to extend it, and then a photoinitiator so that it reacts under UV conditions. We're going to look at the stoichiometry of these materials, as well as really go pretty deeply into the structural parameters. This is what Siltech does, so it's where we spend a lot of time thinking about things and working on things. And finally, we're going to exemplify these with 3D printable materials. We're looking for something with a really good tear strength, tensile strength, but while still being flexible and having great elongation. The experiments are primarily done in a TA rheometer, where we're screening for G prime, G double prime, tan delta, and the cure rate. And then in this study, many of these materials were actually reproduced on the benchtop for mechanical properties. But the rheometer is a great screening tool, which we use quite often. We did 3D print, as I've said several times. These formulations were too viscous for a standard SLA printer. And so we kind of cheated and used an FMD printer, which is a thermal cure, but which doesn't have as many demands on viscosity. And they literally taped a UV lamp to the printhead. Quite ingenious, I think. Okay, so one of the first points we want to talk about is these Q resins are very sterically hindered. So the stoichiometry is greater than you would think from just looking at the empirical formulas. And what we're shown here is the SH to vinyl ratios that we needed to use. And this is the formulation work. Across the top is different formulas. These are the components. The properties are down here. And you can see in this particular case, there are a lot of these graphs. I'm only showing you one. In this particular case, the G prime, G double prime, and tan delta all kind of max out at this ratio of 2.34. So that's repeated over and over again to get those ratios. We did find that the higher the Q ratio, the harder it was to get the reaction to go, and we needed more. And really beyond 30% Q, these formulations didn't work. They're mostly unworkable and in this experiment untested for the most part. So we're going to use the 10Q and 2Q for the most part. Additionally, when we started running the experiments, we found we needed even more. And so this is showing you, these charts are showing you what happens if you increase that stoichiometry even more. Kind of a complex chart, so I'm just going to blow it up. I'm going to blow this region up here. So now we're looking at the 10%, 20%, and 30%. And the delta here is the change when you increase the stoichiometric ratio over what we showed in the beginning. And you see what happens is you do get an improvement in the G prime, G double prime, and cure rate, but you don't get a dramatic improvement. In fact, in this case, you get a reduction in the mechanical properties. But this was necessary to get the reaction to go in any reasonable time. The other thing we looked at was adding more of the reactive diluent. This is that VIN 65K, so the difunctional vinyl. And we've added 10 or 5% in this case with the 10, 20, and 30% Qs. And in general, what happens is your elongation, flex, and tear strength increase, what you expect when you add more extender. And your strength properties tend to go down. So it is a lever that you can pull. It goes in the opposite direction of the previous one, so you can get control of the formulation that you want. But clearly, with this kind of reduction in mechanical properties, there's a limit to how much of this you can use. And 5 and 10% are what we explored. Now we want to look at the ratio of vinyl within the Q resin. So we're looking at the Q's and the T's, but in this case, A plus C divided by B. So the ratio of M to Q is looked at here. So 0.9 or 0.8, we know that when we go to 0.7, that material is metastable, and we didn't really look beyond 0.9. Just we've worked a lot with these materials and would not expect them to perform as desired. So 0.9, 0.8, and then 0.8 with some additional reactive diluent, which we just showed. Here's the results. You get really better physical properties. The tear strength and the hardness are somewhat improved when you look at 0.8, and even more so with the reactive diluent. You do actually have better elongation at the 0.9. I haven't been pointing out, but we're already at 130% elongation. So really these systems are working as we hoped. We're just kind of fine-tuning these properties. So we actually make this Silmer VIN material. It's a commercial product, so we can control the amount of vinyl in there, and that's what we did here, just to see if that was a variable. So the 0.078 would be, quote unquote, off-spec material. We were able to synthesize that and look at the result just with one particular the capto and one particular vinyl silicone resin. And what we saw with increasing that vinyl content actually gave us better tensile strength, tear strength, and what Tom calls twist, which really just means that he can mechanically flexibilize that and twist it in his hands without tearing it apart. So a little bit arbitrary, but probably pretty valuable comment there. Also see the tear strength is going up to 5. We've been around 2 to 3. Elongation doesn't change too much by doing this, and everything else is very similar. So now we looked at the vinyl content in this Q resin, so just the ratio of A to C within the M groups. So we can change this, and they go from 0.6, 1.3 up to 2.5. And the results we get are shown here. We can see that with 1.3 and 1.8, we get an improvement. So the storage modulus, tear strength, hardness, and cure rate increase. But again, we see the elongation go down a bit. We understand with the lower vinyl contents, the elongation is up. With the higher ones, the mechanical properties are going up. In this case, we've added more diluent, so essentially repeating that experiment with a little more diluent and changing that SH to vinyl. Just trying to fine tune these formulations. And what we get here is materials that have tear strength up around 5, elongation into the low hundreds, Sure hardness in the high 40s. So really a reasonably nice material. Again, Tom's sort of subjective comments are nice. Firm with an okay tear, firm with a good tear. So he's liking these materials. In fact, this is one of the ones we went on to 3D print. So just one other point here, looking at the effect of the T groups, so now the ratio of D to B. So putting T groups in relative to Q. And those are shown over here, the 0, 30, and then 50% where we added the diluent because we knew that wouldn't be very tractable. And what you see is that this material gives you better mechanical properties, but lower elongation properties. So by putting the T in, you get better elongation. Sorry, I thought there was another arrow there. So for this reason, we decided to take the T out and see what would happen. And we know that taking the T out really increased the viscosity, but it gave us better properties. So now we're just repeating these experiments with T equal to 0. So, and now we see some really very desirable properties, tear strength up around 7, middle Sure hardness, middle 40s, even up to 50 in these cases, and a very tough, flexible material. So this one is highlighted yellow because we 3D printed that. And then these are just some other formulations that were developed, and we don't really want to talk about exactly the structure of the MQ resin. We're doing some work with customers, and so want to keep that proprietary. But you can see we get some very nice properties again. Tensile strength of 4,000, elongation of 200. My tear strength in the 8s, that's what I wanted to point out. So this is the 3D printing. See, this is the FMD material. We put a nozzle on it, attach the light, and they're just making a bracelet here. Sorry. So this shows, they also did this with a handheld unit. So rather than cure with the light attached, they could just hold the light and follow it behind. See from another direction. It's a really nice looking material. Here they just printed a logo. We didn't license this from DC Comics, so I can't say what that is. It rhymes with Schmatman, if that helps anyone. This is just a better look at these bracelets. A nice, thick, strong, white opaque material. Everyone asks at some point if these materials smell because they have sulfur in them. These materials are not volatile at all. So as long as we strip out the reactants, they're actually essentially no smell. And we had an opportunity to smell these bracelets at trade shows. Most people don't detect any hint of sulfur at all. Even those that do, it's a very trace amount. So in conclusion, we think we understand how to modify the MQT mercapto resins. We know we don't want to use more than 30% Q. I know the T group's lower viscosity, but hardness and toughness suffer quickly if you take them away. The VTQ resins ratio of 0.8 is usually best. 0.9 is actually workable if you want better elongation. The stoichiometry is critical. You can use up to 70% VQ resin to give you better properties. The 65K, it gives you your elongation, and if you need some more elongation and tear strength, you can add up to 5% of that. Increasing the vinyl content of that helps as well, although that's not a big effect. And finally, we developed formulations that were 200% elongation at a Sure hardness of up to 59, a tear strength of 8. We are optimizing this work with some customers, and hopefully we'll have more to say in the future. I should say Siltech isn't looking to sell resins. We would sell raw materials to people who make resins. So with that, thank you for your time.